I'm Elise Roberts, and I would like to welcome you to today's webinar organized by the Section on Statistics in Defense and National Security. Today's speaker is Dr. Derek Tucker, a distinguished member of the technical staff at Sandia National Laboratories. Dr. Tucker received his Ph.D. in statistics from Florida State University in Tallahassee and is currently leading research projects in the area of satellite image registration and statistical functional modeling of optical emissions. His research is focused on pattern theoretic approaches to problems in image analysis, computer vision, and signal processing. In 2017, he received the Director of National Intelligence Team Award for his contributions to the Signal Location in Complex Environments team. Dr. Tucker's talk is titled Elastic Bayesian Model Calibration. Uncertainty quantification methods for computer models with functional response have resulted in tools for emulation, sensitivity analysis, and calibration that are widely used. However, many of these tools underperform when the model's parameters control not only the amplitude variation of the functional output, but also its alignment. Dr. Tucker will present a simple framework for Bayesian model calibration when the model responses are misaligned functional data and demonstrate the techniques to emulate and calibrate a hydrodynamics model using data from a collection of flyer plate experiments and also from a physical model that correspond to tantalum experiments around Sandia's Z machine. A few quick announcements before the presentation. SDNS is soliciting entries for the section's student paper competition for next year's JSM. This competition is open to all undergraduate and graduate students and researchers that are at most 2 years beyond their terminal degree. Entries should be sent to Kim Caulfield by December 15th. DataWorks, the Defense and Aerospace Test and Analysis Workshop, is coming up in April 2024. The 3-day workshop will showcase a combination of applied problems, unique methodological approaches, and tutorials from leading academics and industry practitioners in the fields of defense and aerospace. Interested presenters are encouraged to submit abstracts that apply one of the workshop themes: improving quality of test and evaluation, sharing analysis tools, methods, and collaboration strategies, advancing test and evaluation of emerging and prevalent technologies, and solving program evaluation challenges. To submit an abstract, please visit the DataWorks 2024 website, and the submission deadline is January 26. SDNS is seeking a guest editor for the special issue of the International Test and Evaluation Journal. The guest editor will work with the ITEA production editor from June through September 2024 to ensure timely production and publication of the special issue. If you know someone who would be a good candidate, please nominate that person by sending their name and email address to dataworks@testscience.org. Interested individuals may nominate themselves, and nominees are encouraged to be members of ASA and SDNS. And the deadline for nominations is also January 26th. That concludes all the announcements. And with that, I will hand it over to Dr. Tucker to get started.
All right, thanks everyone. I'm going to give this is recent work that we've been working on here at Sandia, where we've been working on Bayesian model calibration, but where the inputs are functional in nature. This is work that's been doing with Gabriel Huerta, Danny Reese, Justin Brown, and Curtis Schuler here at Sandia National Laboratories, and then in collaboration with Devin Francom at Los Alamos National Laboratory. Give you an outline of the talk today. I'll give you an introduction of the problem we're looking at, kind of why functional data. I'll get into the area of functional data analysis, which is now starting to become mainstream in statistics, with a publication of a couple of textbooks, especially the last one in 2016 by Anuj Srivastava. I'll get into the elastic metric. This is something that I developed with Dr. Srivastava back in 2011 to 2013. I'll talk about that. I'll then get into the Bayesian model calibration using this elastic metric, hence why we have the elastic word up front. I'll then get into some results, a little different than the abstract. We've had some new results that have kind of come hot off the presses. So I'll go through some simulations, some numerical experiments, and then I'll get into some Z-machine equation of state, and where we've been looking at Platinum's equation of state since 10th one, and I'll get into those results. So the question is really fundamental. What we're looking at, and this can be in a lot of ways, is how can you model functions? So we're looking at functional data here, and we have the variability both in time and amplitude. One of the biggest things when we're looking at this is fundamental is a distance. And in statistics, we always forget about, I wouldn't say forget is probably not the right word, but we kind of really forget that, yeah, forget's the right word, that underpinning anything in statistics is having a proper distance. And in having that proper distance, one of the most critical things is that it's symmetric, isometric, obeys a triangle inequality. And I'm going to show here in a little bit why that's not the case, and why we got to be careful that in most statistics, we just use the Euclidean distance. That's how we compute a mean. That's how we get under our standard statistics, and we just take it for advantage of that it's symmetric. But when we get into functional data, the Euclidean distance is no longer symmetric in that case. And really, the differences between functional data analysis and multivariate statistics is in FDA, one develops the theory on function spaces and not finite vector, and discretizes the function only at the final step where you compute the implementation. I tend to follow one of the Ulf Granater, who's a mathematician at Brown, who passed away a few years ago. His mantra was discretize as late as possible. And so even after discretization, when we're looking at functional data analysis, we retain the ability to interpolate or resample as needed. And so the components, as I was talking about in functional data analysis, here is we have those two components I was talking about. And so the first part we have two curves here, the red curve and the green curve, F1 and F2. The aligned functions contain the y variability, for example, or on the right, we have the amplitude variability, or what we call the y variability. This is what happens when we align them. And secondly, if we have a function that we use to align them, say gamma, this is what we call this a warping function. So if we do the time warping of F1 to align the peaks and valleys of F2, that gamma that used to align that contains all of the variability that was along the x-axis, and the line functions contained all the variability that was along the y-axis. And so, for example, if you're looking at the first peak of F1 and the first peak of F2, you can see they're at different times, specifically around 0.6. You can trace that 0.6 on the bottom axis of, so for example, if we look at 0.6, you can trace it here on gamma, and you can see exactly how that alignment was, but that shows the variability. And so these are the two components of variability for functions in R1. Now, classical FDA, if you go back to Jim Ramsey's work, is a lot of cross-sectional analysis. And so what happens in cross-sectional analysis, you ignore the horizontal component, and this often destroys structure. So for example, if we have these two original functions here on the left, which have two peaks, if we just do the cross-sectional analysis and we compute this mean cross-sectionally, you get the purple curve in the right panel, which is actually has three peaks. And the hard part with that, if that's what you compute as your mean, well, we have curves that are coming from a data generating mechanism that has two peaks and a valley. If you compute a mean that has three peaks and multiple valleys, you now have a mean that's not representative of the underlying data generating mechanism. And when you start to think about if you're going to do follow-on analysis such as PCA, where you subtract the mean, if you subtracted this mean from these functions, you then would get functions that don't even look like the original, and you would have incorrect analysis. And we show in previous work back in 2013, if you did put a generative model in this case using this mean, you'd actually create random samples of functions that aren't represented the underlying data generating mechanism. So in Elastic FDA, what we want to do is break up the two sources of variability into the amplitude and phase components, where we compute our means in the appropriate spaces with the appropriate metrics. So for example, if we do this where we align the peaks and the valleys using our elastic metric, and do the cross-sectional mean of those aligned functions, for example, we'll have a mean that's representative of the underlying data generating mechanism. And that's really the underpinning of what we're going to get to talk about today. So if we go into, we're getting into a little math here, into what we want to define as in functional data analysis. So we're going to let f be a real valued function on the domain 0 to 1. Now this can be extended to any domain, easily through a simple transformation, but we're going to keep it on 0 to 1 just for simplicity of the integrals. We're also going to consider only functions that are absolutely continuous. The reason for that further on, but we want to be able to compute derivatives that are on this interval. So that's going to be our definition of a function. We're going to let capital gamma be the group of all warping functions. And so those warping functions I'm going to talk about, we're going to define them as a group. They're going to be the group such that gamma maps from 0 to 1 to 0 to 1. It's fixed at the endpoints, and it's the diffeomorphism. So by stating that gamma is a diffeomorphism, where we're stating that gamma is smooth, invertible, and differentiable, and that its inverse is also smooth and differentiable. And so this is where the concept of elasticity comes in. By defining gamma in this way, gamma is allowed to bend and stretch anywhere in this space from 0 to 1 to 0 to 1. And specifically, gamma is a group. So we have an identity element and we have an inverse, which most previous to a lot of our work, the definition of warping functions, or especially what these align, did not take in this mathematical construct. And so elements of gamma, we'll call these little gamma, act on this function space by composition, by time composition. We'll denote that action, that right action, by f composed with gamma. And so it's common to use the following objective function here at the bottom for alignment, or to compute a distance between two functions. This was work that was originally presented back in the seminal work of Jim Ramsey. Is where if we want to find the minimum, so the minimum of L2 of F1 composed with gamma minus F2, we want to find the gamma that minimizes this L2 distance. The problem with this is if we use the standard Euclidean distance here in this framework, it's not a distance. It's actually not a proper distance function. It's not symmetric. If you swap F1 to F2, you get a different gamma, which is not even an inverse of the original gamma. It's not isometric. And it doesn't obey the triangle inequality. And so if you go to, so with that problem, since it's not a proper distance, if you go to compute means, which fundamentally when you compute a mean, you find this, if you have a set of things. So for example, we go back to the set of numbers and we want to find the mean number. You want to find the element of that set that minimizes the sum of squared distances. Well, for real numbers, that is the Euclidean distance, and the solution to that, the optimizer, is add them together and divide by n. That's the mean. When we get into functional sense, especially where we have this variability, this phase variability, say if we want to find a mean function under this metric, it's not symmetric, and so we can't find a mean in that fashion. And the solution to this problem is the Fisher-Rao metric, and this is this famous Fisher-Rao metric that was originally developed back by Rao to measure the differences between probability density functions. We can use the same, and we can use it here in the functional space as well. The problem with if we do it directly on f, its solution, you can only compute the integral numerically. Now, the solution to this problem is also similar to what Bakhtarov proposed in 1945. What we're going to find here is the square root velocity function here on the first line. So we're going to find the square root velocity function q as the square root of the derivative of the function. So here we have the sine of f dot. F dot is the time derivative of f times the square root. The beauty of this transformation is that the Fisher-Rao distance on this space of the square root velocity function is L2 on Q space, or we'll call this the square root velocity space. And so we can define an amplitude distance here as the infinitum over gamma, where we take the L2 distance between the Q, so the square root velocity transform of F1 composed with gamma times the square root of gamma dot minus Q2. Now, this Q1 composed with gamma times square root gamma dot is just that time composition operator taken through the transform above. Now, this is a proper distance. If you have questions about this, I can provide proofs, but it can be easily shown that this is a proper distance, so it's symmetric, isometric, and obeys the triangle inequality. So we can actually compute distances on that. The second part is we can also compute distances on the warping functions or determine how much of alignment we have. We can actually define a distance here, this dp, or the distance in phase on gamma from gamma identity as the arc cosine here of the integral of square root of gamma dot. And I'll get into that here on the next slide. So if we want to analyze gamma, for example, the problem is gamma as defined is a nonlinear manifold and it's infinite dimensional and we don't know its geometry. So it's very complicated to put a distance on that. So we can take the same trick we actually did above. We can actually represent an element of gamma by the square root of its derivative. So we can say the psi equals the square root of gamma dot. The advantage of this transformation by doing the square root of gamma dot is that the space of all the psi's is a Hilbert sphere. So it's nice, is it's still infinite dimensional, so that's still a problem, but we know its geometry. It's a Hilbert sphere. So the distance between two things on a sphere is the arc cosine, or the distance of that great circle, hence this definition here on the previous slide. We also, because we know its geometry and it's a Hilbert sphere, we can map these elements, these psi's, onto a tangent space, for example, in the diagram shown here on the right, which is centered at gamma ID. And so then we've mapped them into a tangent space, which is even though infinite dimensional, it's still a vector space, and we can do analysis here. Now, the reason I get into this in this part is this will become further when we get into the calibration framework. We'll actually be utilizing these V's, we'll call these shooting vectors, but we can map these gammas up to a tangent space to do more further analysis. And because we know the geometry is a Hilbert sphere, we can go on and off this tangent space. It's 1-to-1 and on 2. And so we can back out these transformations. So utilizing these elastic metrics, I want to get into Bayesian model calibration. And so we wish to calibrate a computer model with parameters theta theta to an experiment that we've done. And so we can compute a computer model, these simulations, we'll call these simulations, over a wide range of theta. And a lot of cases we have here at Sandia National Laboratories and across the national laboratories, the data is functional in nature. And so the data has a phase and amplitude variability. So the figure here on the left, for example, the black curve is from some flyer plate experiments done at Los Alamos. The black curve is the experiment. The gray set of curves is a set of simulations computed from this computer model. And you can see that these curves have variability in both the amplitude and in the timing. And so we want to utilize these elastic metrics, these proper distances, in a Bayesian model calibration framework. So we're going to get some notation within this Bayesian model calibration. We want to let z t of xi denote an experimental measure from the ith experiment. So if we have, so this will be a functional data z, so it'll be an element of f. It's from our ith experiment. Xi in this case here is just some predetermined parameters. They're not theta. These are controlled parameters. Similarly, we're going to let y, for this example, denote a simulation of the ith experiment with input parameters u. So those are the input parameters into our computer model with our controlled input x. So an approach to Bayesian model calibration that's been around for a number of years with functional responses can specify the following models. So we can have z equals y. In this case, we're looking for theta, where y is our simulation plus our delta, where delta is our model discrepancy term with inputs xi, and epsilon just represents all our other error. And so we assume epsilon is normally distributed with 0 and sigma squared e. And so then we have a normal likelihood. And what's been published in literature is then you can create an emulator and you sample from that likelihood and find the optimal theta. The problem with this within the likelihood is you're actually finding the distance between your simulation and your experiment. There's an L2 norm in that multivariate normal likelihood in the way they put it, and it'll suffer from the aforementioned problems with phase variability. So you'll be computing over a distance. If your data is misaligned, you're going to be cross-sectionally averaging it in a lot of ways, and you'll have some problems. because you'll be computing means that are not representative of the data generating mechanism. So if we want to take care of that problem and utilize the elastic frameworks, we can decompose the observation into a line function and warping functions, knowing that it has this variability. So we can take Z and we can find, we can decompose Z into Z tilde, which is the aligned experiment and the corresponding warping function. We also can decompose the simulations in the same framework where we go Y, we can decompose into Y tilde and gamma for YZ. Now, what's critical here in this decomposition, where we're decomposing the experiments and the simulation into the corresponding components, is how you do that. And one conceptually way to think about this is if I have an experiment, a Z, and I have a bunch of computer simulations, I'm going to align all those simulations to that computer experiment. And so then what's left over when I align that is those aligned simulations to the computer experiment give me exactly the amplitude variability, the differences between the computer model and the experiment, and the warping functions give me all the phase differences between the computer model and the experiment. And if you think about it, if we're going to correctly find the correct theta in this model calibration, if we align to the experiment, then we won't have any phase variability. So gamma will be identity upon successful calibration, and that and Y tilde will match our experiment. Now, to facilitate modeling and within this Bayesian model calibration framework, we're going to transform the warping functions into shooting vector space. And so the reason that I showed that previously is we want to be able to compute proper metrics distances between our warping functions. And so we're going to transform those corresponding warping functions we found between the experiments and the simulations. We'll take the square root of their gamma dots, and then we'll map them out to that tangent space. And we're going to call these shooting vectors. So we have this Vxi is the mapping of gamma from decomposing the experiment. So that B is Z to Z here, and then the corresponding same thing for all the warping functions between the simulation and the experiment. So those V's, Y to Z's, and those will be mapped up to the shooting space. And so we'll be operating on the aligned functions and the shooting vectors when we do the calibration. And so what we're going to do is we're going to calibrate the aligned data and the shooting vectors using the following model. Kind of at a high level, you can think about it as we kind of broke it up into two experiments. The one experiment. So if we have one experiment, we have two experiments, but we're going to break in the following model where we're going to look at the aligned experiment. Z tilde is equal to the aligned simulations plus our model discrepancy term plus our noise term, and then do the same thing on the shooting vectors. And so as I mentioned previously, the shooting vector will be identity if the data is aligned to the observation upon successful completion. So if data is calibrated correctly, the shooting vectors will be identity and the aligned functions will match the experiment. You also could, if you wanted to, depending on your data, if you aligned the experiment to one of, you aligned everything to a common reference frame, say one of your simulations, then you wouldn't have that property, but the framework still holds. So to sample from this model, so for each experiment, the likelihood is a Gaussian likelihood. In classic Bayesian model calibration, we fit an emulator, say Gaussian process, BAS, so Bayesian surface splines, or Mars, or pick your favorite emulator to the simulated data. Specifically, when I say to the simulated data, you're going to fit an emulator to the aligned functions and an emulator to the warping functions. We put uniform priors on theta, in our case, and we sample the posterior using delayed rejection, adaptive metropolis hastening. This was implemented using a couple of frameworks. There's on LANL, there's an open source framework on their GitHub. It's been released onto open source called Impala. This was developed by Devin Francom, which allows this Bayesian model calibration framework for multiple experiments. It's a pooled approach. So we've implemented it in that, or we've also done it for those that are familiar with Dakota, developed here at Sandia National Laboratories, which is our Bayesian model calibration framework. you can do the sampling in there, or you can put it in your favorite sampler. Kind of going to show now a simulation of the concept. So the simulation studies where we're going to look at where each function is a parameterized Gaussian PDF given by the function here is fi, where we have theta 1 is parameterized by two thetas, theta 0 and theta 1, where theta 1 kind of determines a little bit of the amplitude, theta 0 determines its location. So here on the left-hand side of the screen, a set of 100 functions were simulated with theta 0 and theta 1 being drawn from a standard uniform between 0 and 1. And so those are the set of gray curves here. The black curve was a specific theta 0 and theta 1 I'll talk about here in the next slide, which we'll treat as our experiment. For also, what tends to happen a lot in frameworks that we deal with at Sandia and across the complex is we have a nuisance parameters. And so we had a third nuisance parameter, theta 2, that was just drawn randomly from from the uniform 0 to 1. And so here for calibration, on the left is if we aligned all the simulations to the experiment. And so what you see here is the black curve is the experiment, the gray curve is the aligning of all the model runs to the experiment. And so we have our line data on the left. We have our warping functions that we computed when we aligned our computer model to our simulations in the middle panel. The black line is for the experiment. So, aligning the experiment to itself would produce an identity alignment. On the right is actually looking at these shooting vectors. So if we map those warping functions onto the Hilbert sphere and then up to that tangent space, we have here the set of shooting vectors, and the black curve, because our tangent space is centered at gamma identity, the shooting vector is all zeros at the center of that tangent space. The blue curves here are actually the draws. The blue are showing draws from the posterior distribution at a 95% credible interval. And so how we calibrated this is we computed that Gaussian likelihood. We actually fit a Bayes emulator to the aligned functions and the shooting vectors. Because this is functional data and the Bayes emulator is set up for scalar responses, we actually utilized elastic functional principal component analysis and fit the emulator on the score space, and then emulated on the score space and then transformed back. And so then we calibrate using the framework as we talked about. We also had a tempering and adaptive MCMC. And so you can see here from the simulations, the posterior draws have a really tight fit around the aligned data and the warping functions. We can then take those posterior draws from the warping functions and the aligned functions and put things back in the original data space. The panel on the left here is showing those original model runs in the original data space. The black is the experiment, and the blue is those calibrated predictions or the posterior draws around the 95th percentile or credible interval, excuse me. On the right, here's the pair plot for theta 0, theta 1, and theta 2. The true value for theta 0 was 0.15. Then the true value for theta 1 was 0.595. Those are shown by the red X's on the pair plot. The red lines are showing the true value around the posteriors. And these are the sample parameters. We have good fit, good estimation. Having a little bit of sampling here on this simulation, it was very tightly constructed. The tempering sometimes sampled. We had like about 15 samples in the chain way out there on theta 0, but overall we had good fit. If we compare this to the standard method, so what has been published in the literature, so if we just take the original functional data, that standard Gaussian likelihood, we fit an emulator and sample from that model, this is what we get. We actually get wider posteriors. We do actually sample at the posteriors cover the true value, but we get much wider posteriors. What's really more indicative is on the left. So on the left is actually, so we got our model run shown a gray experiment in black. The blue curves are the draws from the posterior distributions. So you draw from the parameters and run the emulator. Our draws from the posterior distribution, and we see that the posterior draws are not representative of the underlying experiment. We actually have 3 peaks and some troughs when we should only have really a Gaussian peak coming out of our emulator. So we're actually generating curves from our posterior distribution that are not of the underlying data generating mechanism. So then the question becomes, well, what about discrepancy? This is a common thing. So we're going to repeat the same simulation. I'm going to have this with the same simulation model with the experiment having a timing discrepancy. So where we have here, so here's our, on the left, we have our gray, our computer runs. They don't cover our experiment due to a timing error, which here we have a timing shift to the right. Now there's a couple ways you could handle this if you want us to remove the shift because you knew it. That would also be one. We're going to actually handle discrepancy within the framework. So modeling delta, we're going to model the discrepancy using a set of basis functions in the shooting vector space. Since we know it's a temporal discrepancy in this case, we're going to apply some basis functions and model that discrepancy term delta in our tangent space. So same concept here. Here's if we align, we align the functions. So the line data is on the left panel. The warping functions are in the middle panel, and you can see that the discrepancy is all in the warping function space. So we have a difference between the gray warping functions and the black curve, which can also be seen in the shooting vectors. We used a bash emulator again on the aligned functions and the shooting vectors just as before. Calibrated the framework with tempering and adaptive MCMC just as before. And the blue shows draws from the posterior distribution at the 95th percent credible interval. And we see we have good coverage of both our aligned data and our warping functions. If we combine those back up, we can actually compose those draws from the warping functions and the aligned functions and put it back in the original data space. Again, we have good coverage of our experiment. On the right, we have our posterior draws. We had slightly different true parameters for this experiment. The true parameter was 0.3 for theta 0, 0.1 for 0.2 for theta 1. And again, we had our theta 2 as our nuisance variable. We have good posterior coverage over our true values and overall good sampling. Like this. If we run the standard method, we use the same basis functions, except now we're going to construct we don't have a shooting vector space to do everything in the original data space. We characterize our discrepancy using basis functions. We actually get a lot of small triple peaks around where it's averaging over the model data space. You can kind of see those blue curves here, right here, where things are not great. Here it shows that the true values of 0.3 and 0.2, and actually because we're ignoring the huge amount of phase variability in the discrepancy term and hoping that the discrepancy term captures all of that, we actually have incorrect posteriors. We actually, theta 1 is completely sampled incorrectly, and we have a bimodal distribution sampling. So basically we have some identifiability problems happening when we don't separate out the variability. So now we're going to look at calibration of Platinum's equation of state. We're going to look at calibration of Platinum's equation of state, where the equation of state, the experiment was done using pulse magnetic fields. This was conducted here at Sandia using the Z machine. The Z machine is it actually is the largest pulse power drive reactor in the world. When the Z machine runs, is utilizing more power, generates more electric and magnetic power than anywhere on the planet in a small fraction of a second. What it does is it basically compresses this magnetic field down into space and time, where we can have the material basically change phase over that and the experiment. So we have this magnetic field that hits an electrode. Here shown on the left is this figure here on the left is showing our experimental setup, where we have a magnetic field that induces on electrode and hits the platinum sample, which makes it change phase. And we measure that velocity change basically by having a probe that looks this direction. And so the curves on the right are actually velocity profiles for different experiments of platinum done on the Z machine. And so where the Z indicators, these blue, orange, purple, green, and maroon curves, these are all different experiments that were conducted for platinum. And so our wish is so we have a computer model that we can run a large amount of simulations here at Sandia. We want to know what parameters of that computer model generated, for example, our experiment at Z3561. And so we need to run this calibration. but uncertainty is critical here. And so if we run this calibration framework, and so this plot's showing 3 different equation of state models. The one on the left is what's known as the Vinet model. The one in the middle is the Birch model. These are 2 actually 3-parameter equation of state models that the physics they think describes a lot of what's going on. It captures, and on the right is a non-parametric model that Justin Brown has developed here at Sandia. So utilizing a non-parametric approach to characterize this in the framework. And so we have here we're showing 4 experiments, and then the coloring is showing us calibrating. We actually take those 4 experiments and use those simultaneously into the calibration. And so the blue, green, purple, and orange shaded regions show the 95th percentile, the credible interval around those from calibration for each of the 3. So this is showing for 3 different equation state models. And so we have a good fit between the experiment and the simulation. We have good coverage. This methodology, or this data was originally studied under a different methodology, and we actually have better residuals utilizing this framework than the standard calibration framework of estimating the correct velocity of the curve and the parameters. And actually, we can get more into exactly what is happening. This is comparison to an ILA, which is an integrated Lagrangian analysis. This is a numerical method that over here at Sandia that they've developed to run the physics. And comparing to this numerical method, which is a prediction of what should happen, we have good agreement. This bottom panel down here is actually showing the percent differences between the Lagrangian analysis and the calibration under the Vinet, the Birch, and under the non-parametric model. And actually, the non-parametric model actually has the best fit to the integrated Lagrangian analysis. And so we have very small percentage differences but between those and small percentage of errors. This is something that the physicists here have been extremely excited about. We've been able to use across multiple experiments. And so, for example, we can look at the parameters going into, for example, this is the Vinet model. These are the posterior draws from the Vinet model. And so with this elastic method, we have a tight posteriors over previous methods. And the scientists over at the Z machine have confirmed that the parameters have more physical meaning. They've been excited that we've been able to characterize the density and the bulk velocities of this material, the platinum, which is going to have a huge impact on further analysis of further materials in the complex. What's also an additional nice what we can do within this framework is we can actually look at sensitivity analysis. And so this is looking at 2 different shots on the Z machine at 2 different pressures. The pink curve here is the normalized velocity curve. This is a functional pie chart because we're doing this in terms of the functional analysis. This is looking at the aligned functions. This is the sensitivity analysis. So what you're looking here is the proportion of the explained variance by the emulator after calibration. And so for some of the lower pressure experiments, we're getting over 90% of the explained variance from the parameters that we have input into our model. And you can, but what's nice here with the Z machine is because we're looking at it in a functional nature, you can see exactly along the curve here. This is looking at, so this would be the aligned, this is the experiment, and this is looking at the aligned data, for example. You know exactly along the curve where the parameters have impact along this velocity curve in terms of their explained variance. On the right side, it's not as great for some of the higher pressure. We're finding that so that big gray region is what's all the other unexplained variances, which talks about we're having some interaction terms coming into play. We've plotted out the pairwise interactions. It blows this plot up in terms of coloring and scale and legends, and that starts to fill in the pairwise interactions. But it gives a very large explainability into what's going on with the data. So in summary, what we've done here is we have functional metrics. They provide a global measure of the difference of function in terms of their amplitude and phase. And so it's really critical when you have data that has this variability that you characterize it correctly. And so we've been able to integrate these elastic functional metrics into the Bayesian model calibration framework using this aligned data and the shooting vector representation. And we've really demonstrated the ability on simulated tantalum and actually that's a typo in the slides. I apologize for that. But these platinum equation of state calibration problems, we've also done it on tantalum as well. Some of our earliest results. And so our future work, we're continuing to test this on real world examples here at Sandia National Laboratories and at Los Alamos. We have 2 papers. This is stuff pretty off the press. We have a paper that's currently in revision that we have out to a journal. There's a pre-release on archive shown here. And then there's also a paper that just was accepted to the Journal of Applied Physics, demonstrating these results using this platinum. This paper will be in the next issue next month in the Journal of Applied Physics and will be one on the cover of that. Both of these PDFs, you can find them on archive. You also can find them on my research website, or you can email me at my email address here at Sandia. And with that, I'll open up if there are any questions.
Yeah, hey, Derek, enjoyed your talk. So at the beginning, you motivated functional, at least I understood you to motivate functional data analysis, that when your parameters are not necessarily finite dimensional, when the number of parameters are not finite dimensional. Did I understand you correctly?
So we have parameters like there are finite dimensional that produce infinite dimensional curves.
Got it. Okay, you answered. Okay, very good. And so then the link with the Bayesian analysis there, you're assuming that the number of parameters are finite. So why, other than the fact that you got these really good results and you're coming out on a cover, what was the key thing you noticed early on to show that sort of behavior was useful, was useful to combine with Bayesian methods?
The utilization is where we found it useful with the Bayesian methods is we need to sample those 3 finite parameters, but we need uncertainty on those parameters, right? We want to know exactly what the uncertainty is when we're looking at the model. So if we're looking at, for example, equation of state here for the application, these parameters have very physical meaning, right? What for example, rho naught is the density. K naught is the bulk modulus of the actual material of the platinum. And to the physicists, they want to know what is the value that parameterizes their model that gives them that experiment curve, right? They want to know that value, but they want to know how uncertain are we on that parameter. So if these posteriors are really large, right, and we have a large spread, then we're really not sure that's the right parameter, that we've calibrated the right parameter. Where if the posteriors are narrow around that parameter, we have confidence that we've captured what we think is the true physical parameter that's generating that velocity curve out of the Z machine, for example, right? Getting that density correct has a lot of meaning in further on engineering analysis and construction utilizing that material.
Okay, so that seems to be a case for the Bayesian part, but I'm still struggling to understand why the
with the functional part, to get back to that, is out of this. So for example, back out of the Z machine, we're getting these very large continuous velocity curves, right? And these curves, they have this plot, now I'm realizing you're asking this question, Rich, is not all that great, but what we have here, if I go back to the sensitivity analysis, we have like right here, we have the step functions right here in early time. And what happens for the Z machine is it's a very small amount of time where the magnetic field smashes this material, right? And there's a high change of rate of where that material changes. And that can actually happen at different points in time. As you can see where the pressure is changing, we have it here and here. And they can't predict that exactly given one parameter, the parameter. So the model outputs, which we don't have, I don't actually have a show of because it generates so many curves, but the coverage of the simulations is very akin to, actually, let me go back slide. It will be really good to show this. The flyer plate experiments are very similar. So this is, for example, this is very similar to this flyer plate. You have this sharp change in velocity, but you can see that the computer model is predicting, because it's such a wide grade version, you've got curves out here that have the velocity. So you have a huge discrepancy in the timing and the phase of where that velocity change happens. And so by treating this as a functional data, we're characterizing not only the differences between the computer model in terms of timing of this, but also in the amplitude differences, where you can see that the amplitude, they have it rising really fast, it rising really slow across the computer model. We're able to separate out that variability of the computer model in two separate spaces to where we can find that 1 or 2, 3 parameters more accurately that represents that process.
Thanks, Derek.
Derek, this is Yawen.
Hey, Yawen.
Hey, I have a question on your work. So here you're emulating one functional output. If you have multiple functional outputs, would you suggest doing the procedure for each of them and combine the metrics in some way through the likelihood function?
So the way we've done that, so yeah, you can do it with, if you have multiple experiments, so you can actually handle multiple experiments. You just handle it in the likelihood is how we've done it. We just keep adding on the experiments, and there's a few ways you can take that. If you assume the experiments are independent, for example, you can just combine them in the likelihood. And we've done that so that the Z machine work was actually taking, for example, those 4 experiments on that plot and actually combining them in the likelihood, assuming they're independent experiments.
I see, thanks.
But you can also do it, you'll tend to get, sorry to interrupt, I just have one thought there. When you tend to combine experiments, you'll have, we've seen reduced uncertainty, right? Because you have multiple experiments and you're assuming that you have the same parameters across the experiments, right? Versus doing them individually. But you can also run it individually to really compare posteriors, right? If you have different experiments, you might want to compare those posteriors that are generated from each experiment.
So if, say, your experiment or your functional, your output has more than one function, say like one response is one function and you have multiple functional outputs in that case, how can I still do the same thing?
So the framework would need to be extended. It's a pretty simple extension. You can actually treat them as a multivariate functional data. And the theory then extends. So then if you have a multivariate functional data, then you have a functional data in Rn, for example, and the framework still holds. In that framework, you would just treat it as instead of being in R1, it would be in Rn. And then you still, the square velocity function representation still actually holds in that case. We've derived it. The difference is depending on how you derive your multivariate functional data. In Rn, it has a slightly different mathematical construct when you take the square velocity representation. So the metrics compute is slightly different. That metric's actually derived in that work by Dr. Srivastava in his 2016 book, Functional Shape Data Analysis, but that's all you would change out. For gamma, it would be the same, same representation. So it's a very simple extension in that case. We actually have a case that we're just now working that code out here at Sandia. I just don't have results on it yet. But good question, Yawen.
Thank you, Derek.
Well, thank you very much, Dr. Tucker, for taking the time to share your research that you and your team have done so far. If you're interested in following up with Dr. Tucker's papers, I've also listed them here. And if you're interested in any information about SDNS, the webinar program, student awards, or newsletter, please feel free to check out the SDNS website listed here. We are looking for future presenters for the webinar. You can also find more information about how to become a future presenter at the SDNS website, or you can send an email to me at sdns.amstat@gmail.com. Thank you again to our speaker, Dr. Tucker, and thank you everyone for attending today's webinar.